Hello.
कॅमेरासाठी कसं म्हटलं तुमचं
Hello. So, Umesh sir, shall we start?
Yes.
So, good morning all. Department of Chemistry, Vinayakrao Patil Mahavidyalaya, Vaizapur is organizing 2 days online lecture series on advances in catalysis. And today we have renowned person, well-known person from IIT Indore, Dr. Umesh Shirsagar sir, for his talk. And the today's topic of his talk is Photo-Redox catalysis. So before going to his talk, first of all, I am introducing him. I am very glad and very honored to introduce Dr. Umesh Shirsagar sir. Dr. Umesh Shirsagar sir is currently working as an assistant professor in the Department of Chemistry, Indian Institute of Technology, Indore. He did his PhD from National Chemical Laboratory, Pune in 2011. There are a lot of his research experience is also very vast. He is DST inspired faculty. He did his postdoctoral research fellowship from Israel. He also worked as a project assistant in National Chemical Laboratory. There are many awards and fellowships he got. DST inspired faculty, then PBC Israel postdoctoral fellowship in 2012. He got first rank in Master of Science in Chemistry from Pune University. He also got Best Poster Award. Then he is also editorial board member of Journal of Medicinal Chemistry and Toxicology, Journal of Clinical Pharmacology and Toxicology, then EC Pharmacology and Toxicology. He is also reviewer of various journals like Chemical Communication, RSC Advance, Journal of Medicinal Chemistry and Toxicology, etc. So very vast experience he had in research area in the field of chemistry. He also have number of patents in his credit. So I request Dr. Umesh Shirsagar sir to deliver his talk. Sir, Dr. Umesh sir.
Yes, thank you very much, Dr. Babar, for your kind introduction about myself. Just 1 minute, I'll just share my screen.
Okay.
Is this visible to you all?
Yes, sir.
My screen and presentation is visible?
Yes, sir. Visible, sir.
Okay, good. So, good morning, all you. I really thank you, Mr. Babar, and Dr. Vardeshi, Dr. Sonar for inviting and scheduling these lectures in your. So today I would like to talk about some Photo-Redox catalysis. Detailed title of this talk is Visible Light Mediated Photo-Redox Catalysis, a way towards green organic synthesis. So outline of the lecture. So as you all know, the synthetic transformation or synthetic reactions are the most important part or task, or we can say that the main objective of synthetic organic chemistry. To design the artificial life, for example, synthesis of drug molecule, polymer, material, many things in those these organic synthetic reactions are very, very important. And if you see that traditionally, for that, what we are doing, the nucleophilic reactions or substitution reaction, for example, addition reaction, substitution reaction, elimination. You must have heard the Wittig, Grignard, Friedel-Crafts reaction, or transition metal catalyst, cross-coupling reaction. Many reactions are there, correct? So, majority of these reactions follow three types of mechanism, or we can say that the three types of intermediates, or depends on the what intermediates it involve in that reaction. For example, this ionic reaction. Okay, one is ionic reaction. It follows these ionic reactions where ionic intermediates are involved, and other type is a concerted reactions. You must know the pericyclic reaction. Actually, these so those are the concerted reactions, and other reaction, that is third type, is a radical reaction. Radical reaction involves the radical intermediate, correct? So in today's lecture we are going to talk about this one, and in that also you know that radical reactions can be, yes, yeah. Am I audible nicely? Hello all, am I audible? Hello.
हाँ sir, yes sir.
Okay, good.
Okay sir, you are audible sir, continue sir.
Okay, fine. So this radical reaction can be performed either chemical initiator, in which we are using some chemical initiator, for example EIBN or tempo. So using such chemical initiator, we can generate the radical intermediate. Okay, so we can say the radical initiator also. So actually those reactions are chemically driven. Okay, and second is photochemically. We can generate those radical intermediate using some photosensitizer, or photochemically. So in today's lecture we are going to talk about this photochemical reaction or radical reaction done by this photochemically. Okay, so that is called as nothing but photochemistry. Okay, so that we are going to talk in this lecture. In this lecture we'll see the historical development of this photochemistry, let's say from its early state photochemistry to the then middle eras traditional photochemistry, and then we'll discuss this modern visible light mediated Photo-Redox catalysis. Okay, so these things we will discuss. Then we will also see the importance of this photochemistry. Of course, in any chemistry or any methods or any text, there must be some limitation, drawbacks. So we will also discuss what are the limitation, drawbacks of this photochemistry. But we will also see what could be the possible solutions. What could be the possible solutions for this thing. And then we will see the application of photochemistry in the synthetic organic chemistry also. And shortly, I will tell you what are the further challenges or scope in this field. Okay, so sorry, something is happening here.
तेज कर.
I don't know, slide is not going further. Okay, so just 1 minute. Okay, give me some. Okay, so you must have heard about the green chemistry. What is a green chemistry? Okay, it's actually the, if you see the definition of this green chemistry, the design of chemical products and processes that are more environmentally benign and reduce the negative impact to the human health and environment. So how to do that green chemistry? Actually, this green chemistry is based on or depend on the utilization of those 12 principles, set of those 12 principles, which was developed by the two scientists known as Paul Anastas and John Warner. And this principle ensures the reduce or eliminates of the use and generation of hazardous substance in the design, manufacture, and application of the chemical product. Here are those 12 principles. I'm not going to talk about these principles here in detail, because each principle itself is a one lecture. So, but these two principle, that is a catalysis and design. Actually, this your lecture series theme is a catalysis, correct? Yesterday also you must have heard about many things about the catalysis. So catalysis actually is one of the principle of this green chemistry. So what is that? Wherever possible, we should follow the catalytic reactions, because in green chemistry we should, instead of using the reagents in stoichiometric amount, we should follow the reaction in which there are the we have to use the reagent in the catalytic amount, so that there will be the less byproduct or less wastage of the chemical. And what is the catalyst? That already must have you discuss in yesterday's lecture. So in that we have to use the minor amount of the reagent or in the small quantity, and that will keep on repeating the reactions over the stoichiometric reagents, correct? So that is why catalysis is one of the principle in the green chemistry. Another principle of the green chemistry is a design for energy efficiency. That is, energy requirement should be minimized and process should be conducted at the ambient temperature, or let's say room temperature or ambient pressure wherever possible. And wherever possible, we should use the renewable energy sources like solar energy, wind energy, hydro energy, or fuel cell, correct? So these are the two two principle out of this 12 principle which are connected with this today's topic, that's catalysis and design for the energy efficiency. Talk about the Photo-Redox catalysis, and in which we are using the light energy, and so we are seeing how this light energy is useful for the reaction, and most of these reactions are carried out using some catalyst. So these two principles we are following in this this green chemistry. We are following in this synthesis. So what is photochemistry? If you see the IUPAC definition of this, photochemistry is a branch of chemistry that concern with the chemical effect of light. It means the interaction of the light with chemical substance that initiate some reaction. It's formed some products or whatever the outputs of that interaction of the light with the chemical entities. That is come under the category of the photochemistry. And actually, if you see, this is the chemical reaction which are actually caused by the absorption of some light. Which light? Either it will be ultraviolet light, either then it will be visible light, or it will be infrared radiation. And what happened in that, when this molecule absorbed this visible light, it got to the excited state, and in the excited state it either transfer the energy to other molecule, or it transfer the electron to other molecule, and so that reaction happened, correct? So this reaction has something different than thermally driven reaction. Okay, so thermally driven reaction means what we are doing by, let's say, so maybe those reactions are going by through the ionic mechanisms or concentrated mechanism. So these radical reactions or photochemical reactions are somewhat different than in that, because in this reaction we can access the high energy intermediates, which are very difficult to generate via the thermally driven reactions, correct? So that we can easily overcome large activation energies also over the short period of time, and that is why very difficult reactions also can be done using the photochemistry. So if you see the photochemistry in nature, it's we all know actually this photochemistry's earliest form or old name is solar chemistry, that is reactions or chemistry using the sunlight, natural sunlight. And for your information, I would like to tell you that this solar chemistry or photochemistry occurred on the earth since before the human life came into the existence. Okay. And other natural examples you may be very well known about that, and might be not recognizing it as a photochemistry. For example, photosynthesis in the plant. Okay, plant is making glucose and oxygen. They convert carbon dioxide and water into glucose and oxygen, correct? And for that purpose, they use the chlorophyll as a catalyst, if you know. And this is actually the photosynthesis. Photochemistry. This is the natural example of the photochemistry. Then whatever we are seeing by our eyes, vision, in that also this vision is also initiated by some photochemical reaction. Okay, that involves also the photochemistry. Then vitamin D, which is a very essential vitamin in the body, its formation is also involve the exposure to the sunlight. So by the sunlight, this formation of this vitamin D in the body is started. Okay, this also involves the photochemistry, that's a reaction done by the light. Then in medical field, some certain photodynamic therapies, light is used to destroy the tumor cells. So these are some very important applications, you can say, or you can say that the uses of the photochemistry. We all know that things, or maybe not aware that exactly it is a photochemistry, but actually it involves the photochemistry. Okay, but actual application of photochemistry in the synthetic chemistry started in 1985. Okay, here if you see Giacomo Siamesini, he is a scientist or professor in the University of Bologna in Italy. Actually, he is called as a father of molecular photochemistry. Why? See, in
Hello. हाँ सर, उमेश सर. हेलो उमेश सर. Umesh sir, can you hear me? Hello. Hello. Umesh sir. Hello. Hello. Umesh sir, your voice is not audible. Hello. Hello. आवाज येत नाही सर, काय प्रॉब्लेम आहे? हेलो, हाँ उमेश सर.
I think again you have to make the co-host for me.
Okay, okay sir. Sir, now you are co-host.
Okay. Okay, this is visible, this
Yes,
screen.
yes sir.
And am I audible?
Yes sir.
Okay, I'm really sorry for this.
No, okay sir.
Know how it happened. Like this, I got some call in between, and then at that time
Oh.
this meeting got lived here. Sorry. Okay. Anyway, so in 1912, this Siami seen in his talk on the photochemistry of the future in International Congress of Applied Chemistry, he discussed about the photochemistry and why it is important. So I'm not going to tell about all this detail. In short, I would like to tell you that what he said. He said photochemistry could be a key component of industry in future. It means that he said that instead of photochemistry will be used. Okay. So what are the advantages of the photochemistry? Means if we use sunlight for some purpose, for example, we are using sunlight for the solar heater, water heater, correct, or some other generation of the electricity also. So if we use some sunlight, it does not happen that this energy sun is getting exhausted, correct? It doesn't happen. So it is inexhaustible, and we no need to pay any cost also for that, and there will be no any side effect on the environment also. But that is a very important advantage of the photochemistry or use of the sunlight, correct? Then some other advantages, for example, these photochemical reactions proceed differently than temperature driven reaction, so that we can use that already we discussed in the previous slide, that we can use the high energy intermediate, which are very difficult to generate using the thermal reactions, and we can attain the high energy activation transition intermediates. Processes. Now, in the development of this technology, so if you see at the right side of this slide, you can see this picture of Shyamisin's laboratory in Bologna University. Okay, so actually you can see there. This is his laboratory's gallery. Outside his gallery, he kept many reactions vessel there. Okay, because he has to perform those reaction in under the natural sunlight. Okay, so he was doing such reaction in his gallery outside the laboratory. We can say that it is an outdoor photochemistry using the natural sunlight. So what are the drawbacks of that that technology or this outdoor photochemistry? First of all, and very important drawback is that it requires very long time to complete any reactions. It took the days, weeks, or even months also. If you see that first reaction, it took the 5 months. So this is the very most important photochemistry using the sunlight. Okay, it requires a very long time. Then if you see, if you kept your, just imagine if you kept your reaction vessel outside your laboratory somewhere. So if some strong windstorm come or something fallen on that, some accident happens, so your reactions mixture or reaction vessel will be lost. Correct? That is another drawback. So you cannot keep all your things, reaction vessels outside your laboratory. Then if you keep that reactions open outside, so if your reaction mixture contains some solvent, they are low boiling point, let's say. Okay, so all solvents will get evaporated in the if you keep that your vessel outside for the 5 days, 1 week, 1 month. Okay, that will evaporate. Or if you keep close, some pressure will be exerted in that reaction, that will again have some other explosion risk there. Okay, these are the certain drawbacks of this outdoor photochemistry. But I would like to inform you that despite of all these developments, drawbacks, Shyamisin and his friend and many other people that time of that era has developed and discovered many photochemical reaction which was carried out under sunlight. Okay, but after this, latter of the half of the 20th century, photochemistry moved to the indoor. Means instead of using the sunlight, people started doing the such photochemistry using the ultraviolet light. And that time very advanced ultraviolet lamps were discovered. Okay, with that help of that, people were doing those reactions in the laboratory. Okay, and for your information, I would like to tell you very ultraviolet lights. We can call it as a traditional photochemistry. Okay, almost let's say from 1940, 50 to till last 1990 or 95, 1990, these people were doing this photochemistry, or still they are doing using the ultraviolet light. We can say this as a traditional photochemistry. Just 2-3 examples I would like to show you here, which are done using this UV light, or you can say that under the traditional photochemistry setup. For example, this 2+2 cycle addition reaction. Okay, very complex molecule has been prepared in just one step. Okay, using this ultraviolet light photochemistry. Then another this 2+2 addition reaction that will again give this tricyclic compound, and then cyclopropane ring opening reaction, and again is ring closing to give the another 5-membered ring cycle. If you see, yes, am I audible?
Yes, sir.
Okay, yeah, okay. So if you see these reactions, thermally synthesis of such compound from such starting material is next to impossible. Those reactions will be possible only by such photochemistry only. Okay, so this is the importance of greatness of the photochemistry, that we can synthesize very complicated molecules also very simply. Okay, but again, as I told you, the drawbacks of this outdoor photochemistry, there are the drawbacks of this traditional photochemistry also. So what are those? That we have to use here ultraviolet light. So what is the drawback of that using the ultraviolet light? So ultraviolet lights are highly harmful for human. Okay, highly harmful to the human. So and it required very special setup. We cannot do reaction such as such. Just start the put the some UV lamp and start the reaction. We cannot do that. We need some special setup so that yeah, our body or any other part of body will not be exposed to that ultraviolet light, and we have to take very utmost care. If you, some of you have seen some laboratory in which people have using or doing this ultraviolet light photochemistry in their lab, somewhere in the some part of the corner of the lab, some special utmost care while doing those reactions. And that is why this is one of the very biggest drawback of this traditional photochemistry, that we have to use the ultraviolet light. Another very important drawback is that most of the organic molecule or most of the bond atom, they absorb this ultraviolet light. Ultraviolet light is highly energetic, so all the molecules, all the reagents in the reaction mixture or even solvent also, they can absorb the ultraviolet light, all get excited. So many side reactions can be possible, many side products will form. So we cannot get the one selective product easily many times. So most of the times we end up with the multiple products. And even this reaction, once some radical start, that just keep on going, and it's not easy to control those reactions. And that is why if we would like to perform some photochemical reaction with the ultraviolet light, we cannot predict whether that reaction will go what we desire, or will it form the product what we want. We cannot predict that. So it lacks high predictability in these reactions in terms of product outcomes. So this is the very big, another biggest drawback of this traditional photochemistry, that is non-selectivity and lack of predictability. Then if you talk about some costing things, running cost of these lights is very high. It requires very high energy, and then this price of this light, that lamp, UV lamp, is a very also high. And then another problem is that over the time these lamps get degenerated. Okay, so that again we have to keep on changing these UV lamps. So another, it will cost you more. So because of all this, this traditional photochemistry, for example, using the using the ultraviolet light, it has very little impact in the industry. Okay, so almost there are the almost no application in the industrial scale, you can say. So these are the very serious drawbacks of this photochemistry. So what is the solution for this? The solution is visible light, use of visible light in our now you will say, what is visible light? Visible light is a light belongs to the sun also, or it has a wavelength. We can talk about the precisely of the wavelength. It's from the 400 to 700 nanometer, and below the 400 or below the 300 there is a ultraviolet light. Above the 700 there is a IR light. So now we are precisely talking about the light which has a wavelength between 400 nanometer to 700 nanometer. So we are talking about that. And this visible light range, or this light of this range, is of this solar sunlight contains the visible light, 44%. So we can easily, okay, because again, same like sunlight, it is a readily available, clean, renewable. Okay, we don't need to pay anything for that. Problem is that harnessing of that light means, if you irradiate our organic molecule with the visible light, organic molecule do not absorb the visible light. Most of the organic molecule do not absorb the visible light, but most of the organic molecule absorb ultraviolet light. Just now in last slide I told you that organic molecule, most of the organic molecule absorb the ultraviolet light, because ultraviolet light is highly energetic, but visible light is not that much energetic. So most of the organic molecule do not absorb this visible light. And if our organic molecule, if will not absorb the visible light, then how the reaction will form? So that is the biggest another problem in using the visible light. Then solution for is that, so solution is that we have to use some mediator or agent in the reaction, some agent or mediator, we call it as a catalyst. Okay, that will absorb this visible light and convert it into the chemical energy and will provide that energy to our organic molecules. Okay, so that is a solution for this problem. And what is that catalyst? We can say now this catalyst as a photo-redox catalyst, means that they will absorb the light, visible light. Okay, so that we call it as a photo-redox catalyst. And here we are talking about the use of visible light. Okay, use of visible light for our the reaction. We are using some by means of some catalyst application. So we can say this term now, visible light mediated photo-redox catalysis. Okay. So in visible light mediated photo-redox catalysis, our substrate will be irradiated with the visible light in presence of photocatalyst, photo-redox catalyst. I just written here the PC. PC means photo-redox catalyst. Okay, so this catalyst will absorb the light, this visible light, and will give that energy to our will happen, and we get the product. Of course, it is aiding is acceptor donor, that's something different things. I mean, in same thing that will some electron donor acceptor will need in some reaction, or sometime our substrate itself will act as an acceptor and donor. Okay, so what are the benefits of this visible light mediated photo-redox catalyst? Okay, if you see this, recently visible light mediated photo-redox catalyst has received increasing attention as a potent synthetic technique to generate the radicals, and under the extremely mild condition. Okay, and this radical, this visible light mediated photo-redox catalyst open the door for those synthetically interesting reaction, novel as well as the challenging reaction paths that are difficult to perform a traditional way, or sorry, thermally way. Okay, and even same time, although those reactions might be possible with the ultraviolet photochemistry, but due to the non-selectivity and uncontrolled reaction, they were not so much friendly to do the ultraviolet reaction. So that instead of that, we can use this visible light mediated photo-redox catalyst for the synthesis of those reactions very efficiently using the straightforward way. Okay, and most important is that we don't require any radical initiator. If you compare, I'm comparing this some drawbacks with the chemically initiated radical reactions. Okay, as like in chemically initiated radical reactions, we have to use some EIBN or tempo that we have to use in that reaction. Here you don't require such radical initiator, because in that reactions, if you see, we have to use the radical initiator in the stoichiometric amount. Okay, and here we don't require such a radical initiator. Instead of that, we are using some catalyst, photo-redox catalyst, that will generate such radical, or that will transfer the electrons. Okay, single electron transfer will happen. Then these are the very mild alternative for the traditional way, that is the ultraviolet lights. Correct, very user friendly. What we are using the visible light as a source, that we'll discuss in the next slide. Okay, so this is the benefits of the visible light mediated photo-redox catalyst. Then another advantage is that the visible light. What is that? Visible light is environmentally friendly, sustainable energy source, waste free, non-toxic. Correct, and as like in the ultraviolet light, most of the organic molecule absorb that ultraviolet light. Correct, I told you that in the previous slide, that most of the organic molecule, all the reagent reaction, that's why happening, and most of the organic molecule do not absorb the visible light. And actually it is advantage also, because then all the molecules will not get excited. So only our catalyst will absorb the visible light selectively. So we can get very high degree of selectivity in the visible light mediated Photo-Redox catalysis. So what are the sources of this visible light? See, earlier people were using this household CFL bulb. Don't be surprised. Okay, whatever the household, yes, whatever the surprise household lights, CFL or LED lights in your room, just now also you have started. Okay, those you can use for these reactions because they have that visible light range between the 400 to 700 nanometer. Yes, you are true. Whatever the bulbs, LED bulbs or CFL bulbs you are using your house or your lab or your offices or your colleges, that you can use for these visible light sources. Then people started using the LED lights, the LED ribbons. The LED lights means those ribbons we are using in the Diwali or some other celebration or some other festivals for the decoration purpose. That LED lights you can use to perform this reaction. That is a source of visual light. Then, of course, with this advanced technologies, some industries has prepared specially designed high power LED lamps also. And just now, last year, Merck has invented a device, a special device for this visible light mediated Photo-Redox catalyst. It's also cost almost 5 lakhs rupees. I do not have this. I don't use this also because I'm using still this LED ribbons for these reactions. Okay, household or whatever we can get in the electricity shop. So Photo-Redox catalyst. What is meant by Photo-Redox catalyst? Photo means light. Redox means simultaneously it undergo oxidation as well as reduction. Both things it will do oxidation also and reduction also. It will undergo oxidation and reduction also. That is why Photo-Redox. Okay, and catalyst means we all know what is meant by catalyst and what is doing. Okay, so in visible light mediated Photo-Redox catalyst, there are the three categories of the catalyst generally used. So one is transition metal based polyphenol complex, as I have shown here, some ruthenium, iridium complexes of the polyphenol compounds. Okay, transition metal based complexes also we can use. And then organic dyes. If you see some eosine wire, rose Bengal, fluorescein, these are organic compounds. Okay, they are not transition metal complexes; they are organic compounds. Okay, they're very high. If you see the conjugation and those things, so that they can easily absorb the visible light. Okay, so these are the organic. What is the advantage of using the organic dye? We don't need to use the metal here. Okay, so that again we are going towards the green. Correct. Catalysis plus we are not using the metal because use of the metal is also the one of the drawback. Okay, so wherever possible we should use this catalysts which are free from metal, or reactions we have to design they are free from the metal. So new class of reactions or field of research area came into the picture from last 20-30 years, that is the organocatalysis. Correct. So in that we are using the organic compound as a catalyst in the catalytic compound. So that is another advantage over the metal complexes. So organic dyes are there that also we can use as a Photo-Redox catalyst. And then certain semiconductor also we can use as this Photo-Redox catalyst, such as titanium oxide, bismuth oxide, cadmium sulfide, and many other. Advantage of this semiconductor is that we can reuse that. Okay, earlier this transition metal complex and organic dyes are homogeneous catalyst, and whether this semiconductor is a heterogeneous catalyst, we can reuse it. So that is another advantage. That is, reuse is also the come under the category of the green chemistry. So whatever the catalyst we are using, we are again not wasting that, we are reusing that. Just see the general mechanistic consideration of the Photo-Redox catalyst. So in this, what happened, this photocatalyst PCN I have written here in the ground state, it absorbs the visible light in means 400 to 700 nanometer range. It absorbs that visible light and generate this photochemically excited state, and this excited you can say that electronically excited photocatalyst, it actually involved in this photochemical reaction. And there are the two different ways. Either it will depend on this again depends on the reaction condition. Either it will react with the suitable reducing agent, so that is a donor, so it will accept the electron from that D or donor. It may be substrate also, and undergo the reduction. Okay, that catalyst will undergo the reduction, and then reaction will happen. Okay, and then this reduced catalyst will again transfer the electron to some substrate, or let's say some acceptor, and come to the ground state. Then another way is that this excited photocatalyst will react with some acceptor, or we can say the oxidant. So it will undergo the oxidation. This catalyst will oxidize, and then it will react with the substrate. Maybe it will transfer the electron to the substrate, or it will be transfer the electron to the oxidant, and then reaction happen. And then this oxidized photocatalyst accept the proton from some donor or some substrate, and it will come to the ground state. So these are the two first path. What we discussed is the reductive path. That is, photocatalyst first undergo the reduction, whereas in the other cycle we can call it as the oxidative quenching cycle, in which this excited photocatalyst undergo the oxidation. Okay, and if you say is of the three types. One is a net oxidative reaction. In this reaction, you need, apart from your substrate, you need one external oxidant. Okay, so your substrate will act as a reductant. Then another type is a net reductive reaction. Net reductive reaction, it required the external reducing agent. So here substrate will act as an oxidizing agent. And third type is somewhat complicated. That is a redox neutral reaction, in which you require both oxidizing agent also and reducing agent also, or you don't require the oxidant, external oxidant also, and you don't require the external reducing agent also. In that, your substrate itself will act as a reducing agent and oxidizing agent, or one of the substrate will act as a reducing agent, other substrate will act as a reducing agent, or if there
Sir, your voice is not audible. Umesh sir. Hello, Umesh sir. Hello, Umesh sir. Hello, Umesh sir.
Hello. Yes.
Sir, your voice is not audible, sir.
Yes. Yes. Is it audible now?
Yes, sir.
Is it visible now?
Yes, sir.
Okay. Okay, another early example in 1984, that is this intramolecular cyclization of this azo compound. It was disclosed by the Deronizer in 1984, and in 1984 only Canoillo and this Deronizer reported the first example of photocatalytic oxidation of benzylic alcohol to benzaldehyde. Okay, so photocatalytic, we know that we are doing the oxidation of alcohol with the MnO2 or some PDC, PCC, many other catalysts are there. So instead of that, he first time showed that the benzylic alcohol can be oxidized to the benzaldehyde using the visible light. So these are the certain early examples. This is another early example in the 2004. The cyclization of the oxygen on the anthracene molecule by the visible light mediated Photo-Redox catalyst again. So after this, these are just now we see that these 3-4 examples were known in the literature before 2008, but were not got the good attraction or attention from the chemist. But when these 3 people, this Macmillan, Nice, and this Stephenson and Taesik Yoon published 3 simultaneously, individually they published the 3 papers in 2008 and 9, and after that only this was started. Macmillan demonstrated that he actually performed the organocatalytic asymmetric synthesis using visible light mediated Photo-Redox catalyst here, if you see. Okay, in 2008 he published this one. Similarly, Taesikun published the 2+2 cycloaddition reaction using the visible light mediated Photo-Redox catalyst. Earlier, these reactions were carried out using the similar type of 2+2 cycloaddition to form the cyclobutane or 4-member ring using the ultraviolet light photochemistry. But here, Taesik Yoon first time showed that the such 2+2 cycloaddition reaction for the generation of this cyclobutane ring can be possible using the visible light mediated Photo-Redox catalyst. And this Stephenson showed the dehalogenation reaction using this photochemical reaction. Just replace this halogen with the hydrogen with using this visible light mediated Photo-Redox catalyst. And after these 3 papers, all people this visible light mediated photochemistry got attracted from the various chemists or chemistry people, and then this dramatic increase and escalation of this photochemistry was started after 2018. And if you see, most of the biologically active compound or drug molecule or natural product contain the nitrogen. Okay, so that's why great attention was given towards the generation of amine radicals, where the tertiary amines was used, and using the Photo-Redox catalyst. If you see in the mechanism, here just one mechanism I have shown here, iridium photocatalyst using the household light get excited, and this excited photocatalyst abstract or absorb the or get accept the electron from this amine. Amine act as a donor here, and it will generate this amine radical cation intermediate 2. And this intermediate 2, its alpha hydrogen again now in this structure is highly labile, and then again it will also undergo the homolytic cleavage and form this amine cation 3, and that again easily get attracted by the different nucleophiles. So in short, it's something like a alpha CH activation of the amine. Okay, using the Photo-Redox catalyst, simple nucleophile can be attacked over that amine, and you can get the that nucleophile gets substituted at the alpha position of this amine. Stephenson in 2010 published the Aza-Henry reaction, in which this benzylamine at the alpha position, he using the iridium, he substituted or introduced the nitroalkane moiety on the alpha CH bond of this amine compound. Okay, then this is the oxidative Strecker reaction. Strecker reaction, that is the introduction of the cyano group at the alpha position of this amine. This was done by the Magnus Rupin, okay, in 2011. Okay. Very simple reaction, very easily it was synthesized, but otherwise it's very difficult to synthesize such compound, okay, from such substrate. Then other nucleophiles also, for example, this cyclobutylone and this indole, they also introduced on the alpha position of the amine using the Photo-Redox catalyst. After this, carbon phosphorus bond also prepared using this Photo-Redox catalyst. Apart from this, this acetone, let's say, or this acetylene and CF3 group also easily introduced at the alpha CH bond of this such type of tertiary amines, okay, using the visible light mediated Photo-Redox catalysis. Until now, if you whatever the examples we have seen, in which most of the times we have seen catalyst use, that is a photocatalyst use, was a transition metal based. After that, in 2011 somewhere, Burkhard Koning started using of the some organic dyes, that is, for example, this eosin as a Photo-Redox catalyst. Instead of transition metal complexes photocatalyst, he used the organic dyes or organic molecule as a photocatalyst, and he showed so those already known reactions. I mean, if you see here that Strecker reaction, that is the application of this introduction of the CN or nitroalkane or similar carbon phosphorus bond, he again showed that this reaction can be possible using the organic catalyst. So it's no need to use the those transition metal based photocatalysts. So these are the organic photocatalyst driven reactions, visible light mediated organic photocatalyst driven reaction. So this is again another step towards the green synthesis. Then CH arylation reactions was also discovered in the 2012, in which such diazo compounds was used, and these diazo compounds with the help of this excited eosin Y catalyst undergo the eosin Y undergo the reduction, oxidation, and we can generate the aryl radical. This aryl radical react with our substrate, and then further oxidation gives the desired product, that is a CH arylation reaction. Okay. Then another field started, that is a merging of the transition metal catalyst with the photocatalyst, that is a dual catalysis. For example, in the CH activation. So CH activation, CH will be activated by the palladium catalyst, our normal CH activation reaction, and other group will be generated, or other reactive intermediates will be generated with the help of photocatalyst. So that has some distinct applications, such as we don't require high heating, we can perform reaction at the room temperature. Okay, so these are the advantage of this dual catalysis. So, and that is also the application people have shown, where this we can say that the merging of the transition metal catalyst with the Photo-Redox catalyst. My group is also working on the Photo-Redox catalyst, and we have developed eosin Y mediated Photo-Redox catalyzed oxidant and reductant free net redox neutral reaction, in which we have done the vicinal thioamination of this alkyne via the radical cascade reaction. If you see this compound number 3, that is in 3-sulfonyl indoles. At the right side, you can see there are various biologically active drug molecule, and in which such moiety is present. And so we have developed this radical cascade reaction, in which this alpha azido alkyne will reacted with this sulfonate ion in the presence of visible light. We have used here eosin Y as a catalyst, as a photocatalyst. If you see the substrate scope, not only aryl but here one alkyl sulfonate also give the almost 48% yield if you have the product number 3p. And apart from aryl alkylate, alkynes also work in this reaction. For example, 3QR, 3S, and 3T compounds. Okay. For these reactions, to see the mechanism of this reaction, we perform certain controlled reaction in which we perform the reaction in the absence of photocatalyst and light. And we observe that there is no formation of the product, which suggests that these reactions works by the photocatalysis. Okay. And when we perform the reaction in presence of certain radical quenchers such as a tempo, BST, we did not observe the formation of desired product. It suggests that there is a formation of radical. If in any reaction, if radical is the intermediate, if you perform that reaction in certain radical quencher, reaction will not happen, or you won't get the desired product, because whatever the radical intermediate is forming immediately react with that the radical quencher. And if your radical intermediate is not available for the reaction, you won't get the product. So when we perform the reaction in presence of this radical quencher, that's a tempo and PST, we did not observe the formation of product. We perform this reaction in presence of external oxidizing agent, external reducing agent. We did not observe the formation of product. That suggests that reaction is net redox neutral reaction. Okay. And to rule out the formation of nitrine intermediate from the azido compound, it is also known somewhere that azido compound photocatalytically or any radical type chemical reactions, it undergo the nitrine formation. So whether in our reaction nitrine is generated or something else, to check that, we perform the reaction in presence of alkene to trap that nitrine intermediate, but we did not observe this, that type of product, which suggests that nitrine is not forming in our reaction. So on the basis of all these experiments, we suggest this following mechanism, in which this eosine Y catalyst absorb the visible light and get excited, and this excited catalyst absorb the electron from this sulfonate ion and generate the oxygen center radical 4. Okay, and this oxygen center radical 4 intermediate rearranges or resonate between the intermediate 5, that is sulfur center radical, and this sulfur center radical radioselectively attack over this triple bond, that is ortho-azido alkyne compound, and generate the olefinic radical intermediate 6. Okay, and then this olefinic radical intermediate 6 react with the nitrogen, that nitrogen of the N3 or azide, with the removal of the N2, generate the radical nitrogen. Okay, now this center radical 7 absorb the electron from this reduced form of the eosine Y, so that eosine Y go to the ground state. Okay, and this N minus will generated, that's intermediate 8, and this will absorb the proton from the water, or when we do the workup, and it will form our desired product. So this is a mechanism of this reaction. We can call it as a radical cascade cyclation reaction. Okay, so just now we are seeing here this three sulfonyl indols are the very important scaffold present in the various biological active compound. Similarly to that, 3 sulfonyl indols, that is a SAR or S alkyl groups present on the third position of indol. They are also the very important substrate present in various biologically active compound, as shown in this square bracket here. These are the something, let's say, cytotoxic or CRTH2 antagonist or anti-HIV protease molecule. So such moiety is also important. So we extended this radical cascade cyclation reaction, in which we perform this reaction instead of sulfonate ion, we use the thiol here, and we could easily get the this 3 sulfonyl indol products 10. Okay, various molecules we prepared. Okay, this is another project. as we know that benzothiazepine compounds has a very good antibacterial activity, and aryl thiocyanate has a very good application in the agrochemical. They are a very good pesticide. So we thought and design benzothiazepine in which it will have the thiocyanate moiety as the third position. So itself benzothiazepine is the aryl moiety or aromatic compound, and so this compound will have it may have the both the activity, that antibacterial also and agrochemical activity also, that's anti-pesticides, pesticidal activity also. In that sense, we designed this compound and thought we can easily synthesize this type of compounds with the help of similar like a previous radical cascade reaction. For that purpose, we synthesize compound 9, that is ortho thiomethyl alkyne, and reaction of this ortho thiomethyl alkyne with the ammonium thiocyanate in the presence of eosin as a photocatalyst, in presence of visible light, we could easily generate this product. Okay, various substrate we have prepared. If you see the mechanism of this reaction, similarly like previous reaction, this excited photocatalyst, after the absorption of the light, it abstract the proton from this thiocyanate, and from the reduced form of the catalyst, that is eosin Y dot radical, and this radical thiocyanate intermediate A react with the our substrate 9, that is it reduce cellularly attack on this triple bond and generate the olefinic radical B, and then intramolecular cyclization generate the intermediate C, and oxidation of this intermediate C from the intermediate D, that is a sulfur cation. And once this sulfur cation forms, the sulfur methyl group become very labile, easily get break and form the corresponding product. So these are the some recent work we done in the photocatalyst. Few of the work we done in the photocatalyst. Unfortunately, from the last year, our lab is almost closed. We could not perform the work. All the students are at the home. So just now this year, 2-3 months, they came back to the campus and they started working again on the new projects. That's why in between 1 or 2 years, we don't have any sizable, or you can say that results which I can show you here. So that's why I have shown here some results in the published in the 2018. So with this presentation, or with this work, I would like to conclude this topic. So in conclusion, I would like to inform you, I would like to tell you that we have discussed what is meant by photochemistry, its historical background, how the outdoor photochemistry is there, what are the drawbacks of that outdoor chemistry, how it was change with the indoor photochemistry, in which we have used the ultraviolet light, and what are the drawbacks of that ultraviolet light, and then what are the solution that we have discussed, that is a visible light mediated photocatalysis. For that purpose, we have to use the Photo-Redox catalyst as a compound or mediator that will absorb the visible light and form the product. So major benefit of this visible light mediated photocatalysis is a mild and environmentally friendly conditions. Okay, that is why very high research already has started or geared up towards the discovery of various photochemical reactions for the very difficult reactions also. Apart from synthetic chemists, this visible light mediated photocatalyst is also attracting the attention from researchers in drug discovery, chemical biology, and material science also. Again, if you remember one slide, we have discussed on the merging of photocatalyst with the other catalyst systems, such as a dual catalyst. Okay, that is also the very great good field started again. We are also started working on this merging in the Photo-Redox catalyst. As compared to this all the development, there is very less development or application of this visible light mediated Photo-Redox catalyst in the asymmetric synthesis. There is a requirement, or in future there is a scope, or this is a challenge that we should have the more and more application of this visible light mediated photocatalyst in the asymmetric synthesis. And again, still now we are using the visible light. Visible light means the light in the wavelength range of 400 to 700 nanometer, and we are generating that, or we are getting that light from the certain light source, that is a household light or LED light or certain lamps. Okay, still we are far from application or use of direct sunlight in this visible light mediated photoredox catalyst, because we know that sunlight is already contains 44% of the visible light. So in future, many people are trying to use that sunlight. For that purpose, we have to design such a photocatalyst that will easily and quantitatively absorb that visible light part from that sunlight, and it will give the it will form the happen the various photochemical reactions. Okay, so that will be the really great idea, or ideal synthesis, green synthesis. You can say that that reaction quickly, less time, no, very good selectivity, mild condition, and we have to use the sunlight as a energy source. That is a future, or you can say that the a challenge in the future for this, or you can see in the way of scope for this visible light mediated photoredox catalyst. Okay, so with this conclusion, I would like to stop here today. First of all, I would like to thank this organizing committee, Dr. Pardeshi, Dr. Sonar, organizing such events, because in this pandemic situation, although many places, colleges are not started, or even university institutes are not started, so in presence or offline lectures are not possible, correct? So with these online things, this knowledge transfer or knowledge sharing will not hamper. So still we can learn many things through the online lectures. That's why I really thank this organizing committee and coordinator for organizing such events. Okay, so thank you all for this your nice patience to listen all these things. If you have any questions, you can ask me. Thank you all.
Thank you, sir. Participants, if you have any question, you can ask to Dr. Umesh, sir. Any participant, if you have any doubt, any question regarding today's talk, so you can ask to Dr. Umesh, sir.
Sir, very good afternoon. What is
Good
the role
afternoon.
of use of dye in the photo reduction synthesis?
What is the use of dye? Correct?
What is the role of dye in the photo reduction?
Yeah, role. Okay. These dyes actually act as a catalyst. As I told you that organic molecule do not absorb, most of the organic molecule do not absorb the visible light. So that is a problem. Okay. So what was the solution for that? We have to use some mediator, any mediator. Mediator, we can call it as an agent, or we can say more scientifically catalyst, that will absorb this visible light and give that energy to the organic molecule. Correct? That we discuss. So here catalyst, either metal based complexes will be the catalyst, then such organic molecule that will absorb the energy. Or I said that most of the organic do not absorb the visible light, but there are certain organic molecules such as this eosin Y, or those are something like a dye. If you know the dye, why dye is showing the color, because they are having very long resonance or this conjugation, and due to this conjugation they can easily absorb the light, and that's why they reflect also light. Correct? So we can call it as a dyes. Correct? So these dyes can easily absorb the visible light, and as they absorb the visible light, they can also act as a catalyst. So here these dyes are acting as a catalyst. Their role is being a catalyst, photocatalyst. Okay, like a transition metal complexes photocatalyst.
Okay. Any doubt? So I think there is no doubt to any participant. So in the second day of this online lecture series, today we have Dr. Umesh Shirsagar sir from IIT Indore. His topic was photo-redox reactions and catalysis. He divided his talk in two parts. In the first part, he introduced regarding photochemistry. He also discussed historical development of photochemistry, importance of photochemistry, limitations of photochemistry, then what are the solutions to these limitations, applications of photochemical reactions, and what are the further challenges. So these points he had discussed in his first part. In the second part, he discussed visible light mediated photo-redox catalysis. And in this part, he discussed the benefits of visible light in photo-redox catalysis. Then he discussed the properties of photo-redox catalyst. Then he also discussed the general mechanism of photocatalysis, photo-redox catalysis. And then in the last point, he gave various examples of photocatalytic reactions in his talk. So on behalf of Department of Chemistry, Vinayakrao Patil Mahavidyalaya, I am very much thankful to Dr. Umesh Shirsagar sir for his wonderful lecture on photo-redox reactions and catalysis. So thank you, Dr. Umesh sir.
Yeah, thank you all.
Thank you, sir.
May I leave the meeting now?
Yes, sir. Yes, sir.
Yeah, thank you.
Thank you, sir. Thank you. So participants are requested to please fill the feedback form. Feedback form link is shared in a chat box. All the participants are requested here to please fill the feedback form of the today's lecture. The link of the feedback form is shared in a chat box. Thank you.